Hello, let's continue our Sudoku adventure with I'm Not Weird, I'm Just a Little Irregular by the Asylum. This is just a plain old irregular 6x6 Sudoku. So let's go over the rules. So in each row, each column, and each bold outline region, we're placing the digits 1 to 6 exactly once each. So we don't have our normal 3x3 boxes, but we still have 6 regions that are designated by these bold outlines, and each of those 6 regions has 1 to 6 in it. That's it. Those are the rules. There's a link in the description if you'd like to try the puzzle yourself. And I'm going to get started right now. Okay, so often with irregulars, it's good to think about kind of the geometry of things, right? The shape of the actual irregular regions. So for example, we have this shape here. So here's a really nice generic way to evaluate this stuff. This row, I'm going to make green. And this region, I'm going to make purple, and there's going to be overlap. So some cells are purple and green. Now we know that green, these 6 cells that are green, has 1 to 6 because it's a whole row. We also know that purple has 1 to 6 because it's a whole region. So purple and green have the same digits as each other. Now if I remove this cell from both purple and green, because it's labeled both purple and green, I can remove it from both. Whatever digit that was has been removed from both purple and green. So purple and green still have the same digits as each other. I can remove the 3 and 6, and now I know both purple and green have the same digits as each other and don't have a 3 or 6. I can also remove this one. I don't know what digit it is, but I know that I've removed it from both purple and green. So purple and green still have the same digits as each other, which means that we need a 1 in them and we need a 4 in them. So this is a 1 and this is a 4. So that's a nice way. It's kind of a if you want the technical terms, it's a set-based approach to show law of leftovers. if you want to look up those terms, but I'm not going to get too far into it. But that's kind of neat thing we can do. So you can kind of eyeball this when it's one region against one row or one column. We need the 2, 3, 4 to end up in this region, and they don't go here. So this ends up being a 2, 3 pair. But there was something I noticed about this region, which is going to be important for this 2, 3 pair, which is that where does 2 go in this region? Because 2 can't go here and 2 can't go here. So 2 ends up in one of these 2. And that is going to point, because if 2's in one of these 2 cells, it can't be anywhere else in the row. So this ends up being a 3 and this ends up being a 2. And we know that these are going to be just the remaining 3 digits for the row and for this region. The 1, 5, 6. I'm not going to mark that yet. I think it might be fun to just see how much geometry we can get with minimal markings. So let's see, what are the remaining 2 digits here, though? We need a 2, 5. So this 2 looks down. Yeah, so 2 can only go here, and that's a 5. And that does place the 2 in this box here. The remaining 2 digits here are the 3 and 5. So let's see. By the way, we could have gotten these 3s in an interesting way. Let me talk about that because, this is a pure irregular, so it might be a good learning experience to learn things you can do in irregular. So what I've done is I've highlighted in green 3 rows. So there are 3 sets of 1 to 6. There's 3 1s, 3 2s, 3 3s, etc., all the way up to 6. Now here's a whole region. This is 1 to 6. Here's a region, and here's a region that I'm making purple. The purple region also has 3 sets of 1 to 6. So this is still just a set-based approach to the law of leftovers, but I think it's a really nice way to think about it. And so anything that's both green and purple, we can remove, and that tells us that these 2 digits are the same, and so that would have immediately let us place this 3. So I don't know if there's more like that, but those are kind of ways to associate digits that have to be the same as each other in an irregular, and that can often be helpful for your solve. So a good way to kind of find those is to just in your mind, like, keep adding rows or columns until you think you've like encompassed like here, right? I've added 3 columns here and I've encompassed 2 full irregular regions. And so if I remove those, what we can actually see is that this is kind of a virtual irregular region. This has to have 1 through 6 in it because I highlighted 3 columns, which had 3 sets of 1 through 6, and then I removed 2 sets of 1 through 6 from it. And so this still needs 2 through 6. So where does 2 go in the green? Now I'm solving this in probably a way that you don't need to, but I want to kind of demonstrate how you can think about these. Hopefully, I'm not going to say that again, but so the remaining digits that we need here are 3, 4, 6. I can't really do anything with that, but yeah, kind of fun ways to look at things. Oops, I didn't mean to clear the digits. I meant to clear the color. Okay, well, let's take a more straightforward approach to the rest of the solve, but let's see. I'm just going to start penciling now. We need a 3, 5 pair here. Ah, right. So there is a 3 in this region already, which I hadn't noticed. So that's a 5 and that's a 3. Finish that column. We get a 3 in the corner. We know that these two digits are the same for reasons we've talked about, right? We can compare this row to this region, and these two end up the same. So what can they actually be? They can be a 1. They can't be 2, 3, 4, 5, or they could be 6. So they're the same digit, and they're a 1 or a 6. Where does this... Okay, I'm actually going to color this green. These are the same digits as each other. Where does green go in this box? It can't go in the same row or column, and it's not a 2, because it's 1 or 6. So green ends up right here as a 1 or 6. Actually, where does 5 go in this column? This 5C's here. This is 1 or 6, so the 5 ends up here. This is the other 1, 6. I'll make that purple, because why not? Always good to know what the other of the pair is and where that goes. So where's purple in this row? Because purple can't repeat in its own region. And it's not 3 or 2. So purple ends up here as a 1, 6. Oops. Wrong mode. So that tells us what this digit is. This has to be a 4. We have the 1, 6 pair in this row. We're missing the 3. So that's a 3. We have 1, 2, 3, 6 in here. This is 4, 5. Same for the row. And this 5 tells us the order. That's 4, that's 5. Here we need a 1 and a 6. This 1 tells us that's 6. Sorry, other way around. It tells us that's 6 and that's 1. This is our 4. This column we need 3 and 6. This 3 tells us that's 6, that's 3. And that tells us all the greens are 1 and all the purples are 6s. All right. 1, 2, 3, 4. We need 5 and 6 here. This 6 says that this is 6, that's 5. This is a 5 here. Last digit's a 4, and we're done. Cool puzzle, Asylum. I'm glad I was able to show some like irregular techniques. The concept of law of leftovers is usually what that's called, but you can apply kind of a set-based approach to analyze it if that's easier for you to understand. Showed a few different ways to approach that, showed a few different ways to think about digits having to be the same as each other and how that can help. So I don't know how much of that was actually necessary to solve the puzzle, but I enjoyed being able to demonstrate that. So I hope you enjoyed this as well. Let me know how you did. And if you did enjoy it, why not leave a like, subscribe, and a kind comment below.